So today we are going to be covering the alkyne. And alkynes, the simplest of which is called acetylene, and it's just drawn like that with a triple bond there. And we write acetylene, which is the common name for the actual molecule. The IUPAC name is, of course, not acetylene. And acyl is the old-timey term for two carbons, I guess. But ethyne with a Y, right? A double bond that's ethene, single bond is ethane. All right, and many of the reactions that we're going to talk about with alkynes are very similar to alkenes, and they observe the same sort of rules and produce similar products. Not all the time, but pretty reliably. Now, to name more complicated alkenes, it's pretty simple. Like with all things, let's just move this over here. With all things you do, you find the longest chain. All right, and so you've got an internal alkyne, the CH3. You can count 1, 2, 3, 4, 5, 6, 7, and so this is a hept. And there's the start of the alkyne is at the 2 position, and you just add Y and E onto the end of it. Now, if it's a bit more complicated, right? If, say, for instance, there is a, say we put a bromide here, right? Then that's no longer the right term. Then this is suddenly 5, 6. We want to consider that, all right, the first substitution is definitely going to be at the 2. So we got a 2 here. All right, and alphabetically, it's BR. Right, a second. We're going to put BR here. All right, 1, 2, 3, 4, 5, 6, 7. All right, 2 there. So this is going to be a hept again. All right, 7 carbons still. But the again, it's going to be a 2 heptine. And it's going to be a 5 bromo. 5 bromo, 2 heptine. Pretty easy stuff. All right. So what are the characteristics of an alkyne, right? What makes them tick? And like I said, it's not extraordinarily different from an alkene, right? So you've got a carbon and a carbon. And these are sp hybridized. So that means that they've got a p orbital. It comes up and down. And they got a second p orbital that comes out and away and out and away. So these have an awful lot of electron density. They have electron density going through here on the sides, and they have electron density on the top and on the bottom. And essentially, they are very close together, right? So this could have a, let's just say this is acetylene. That's coming out here, and that's coming out here. Our bond, our triple bond is formed from electron density above and below, and then to the left and to the right. All right, and that of course means that all that electron density connecting everything together, this bond length is much shorter, right? So if we remember, carbon-carbon bond length is about 1.54 angstroms. Carbon double bond carbon length is about 1.33 angstroms. And then the triple bond length now is the shortest of them all, 1.20 angstroms. All right, so that electron density does make the whole bond get much shorter. All right, and now there's a lot of energy in this molecule, right? So acetylene, you're probably familiar with acetylene. They throw them into, you use them in acetylene torches, and it burns at like 2,800 degrees. It is extraordinarily hot. burning and decomposing, and releases a ton of energy because there's just a ton of energy in this bond, right? So it takes a lot of energy for it to burn out, all right? Now the hydrogen here is not super duper different than normal hydrogen. So the CH bond here, and we're going to talk about the CH bond in a lot more detail. That's a 1.06 angstroms. That is actually a bit closer than the ethene and the ethane. So the ethene is 1.08 and the ethane is 1.09 angstroms. And that's going to have a bit of an effect on the acidity of that. And you'll notice, of course, that there is this cone of like electron density that's going around here, right? So you've got like an enormous amount of electron density. Let's pick a different color. Let's just call this red. That there is just this sphere, if you will, of electron density coming out and through here. And it is a lot of electrons that make up this system, all right? And this is a very sp hybridized carbon, both of these. Sp means that they have a ton of s character, right? Because it's like 1p and 1s, so that's 50% s character. And s character you can associate with electronegativity. So the more s character something has, the more electronegative it is. And that means that it really loves these electrons, which is why that bond is shorter, because that carbon is getting more and more electronegative, all right? And as a consequence, these protons actually are becoming more acidic, right? So the acidity, if we compare the acidities of our hydrocarbons, we'll remember that so we'll call this up here bond lengths. We'll call this acidity. All right, so the acidity of a CH, CC single bond, CH, right, has 25% S character, right? Because it's sp3, 3 P's, 1 S, not a lot of S character. Its pKa is pretty ridiculous. Its pKa is like 50. All right, so the likelihood of that hydrogen coming off in the presence of any base is extraordinarily low. It requires a tremendous amount of energy to produce that kind of base, which you can abstract with strong metals. All right. Now, if we talk about alkenes, you'll remember that these protons, so that's that proton, okay, it's still not very basic. Well, I'm sorry, it's still not an acidic proton. It's sp hybridized, right? So it's a little more basic. It's a little more acidic. I'm sorry, I keep saying that word. And you get a pK of 45, 44. That's not an acid. So you don't deprotonate these things very easily. It takes a lot of energy, you know. A good benchmark is if we consider ammonia, NH3, right? Ammonia we associate as a base because it's got this lone pair, it goes and deprotonates. I mean, that has protons, and those protons can be popped off with a pK of about 35, which means you also need a pretty strong an acid, basically a metal that will abstract hydrogens, will abstract protons pretty easily in order for you to get that off. Now, alkynes are actually below that. They are pretty, in contrast, acidic. And these protons right here have a pK of about 25. So what does that mean? That's a pK of 25 means that you can probably deprotonate that with regular bases. So you can actually deprotonate it with the lithiated or the strong bases that we discussed in the prior chapter. So if you lithiate that and make your lithium diisopropyl amide, then you can take that off. And that's a pretty easy commercially available base. You can also remove it with potassium hydroxide or other really strong bases because you'll remember that the the alcohol proton actually has a pKa of about 16. So that is a, you know, acidic proton by all measures. But the difference between these two, while several orders of magnitude, is not so large that this is a particularly onerous proton to pull off, which is actually fairly useful in creating carbon-carbon bonds, because if you deprotonate an alcohol, then you have an RO minus, and that can go and do all kinds of stuff. But if you deprotonate this, then you have an R carbon-carbon minus, and that's a carbon nucleophile or a carbon base. And now you're kind of off to the races and making new carbon-carbon bonds. So where does how do you make these? How do you make triple bonds? That's an interesting question. Well, as you can imagine, there are industrial processes that form ethines, right? So you can form them from, if you take coke and lime, so basically carbon and a strong calcium base from lime, you end up making calcium carbide. All right, it's a organic starting reagent. You add a little bit of water from steam, and you heat it up in an electric furnace. So these are thousands and thousands of degrees. You will end up with acetylene. And of course, if you look at your stereochemistry here, you're going to end up with calcium hydroxide. And you drip water. It's of course extremely high temperatures. Now you'll probably remember that, you know, if you could make a double bond, you can make a double bond by doing an elimination. So if you started off with something that was, you know, chloride here, and you added a base, you could make a double bond, right? That was something. But you can also do the same thing if you have a chloride here and a chloride here. So of course, you're going to have to have a hydrogen at all these points. So there's still a hydrogen here. And you got a high chloride here. Oh, I've added so many chlorides. That's going to have to be a hydrogen as well. You can go through one elimination. So, you know, you strike your strong base and pop that off, and that goes down there and kicks off the chloride, and then you end up at this, and that's actually a pretty easy reaction to do. You still have a hydrogen, you still have a chloride here. This reaction is a little bit tougher now to come off here, so it's going to be a slow reaction, but it's still possible. You can still come over here, grab that proton, kick that down. Now I've got a triple bond as that comes back off, and you've got your, what do you call that? 1, 2, 3, 4, 5, 6 hex 3-hexyne. And so that's one way to do it. You'll note that I drew it up here. Let me color these chlorides in green. I drew these chlorides in a vicinal position, right, side by side, and that gave you this compound over here. It also works if they are geminal, and so we've talked about this a bit before, that instead I have my chlorides on the same side, and the two hydrogens are now over here, because I do have to eventually produce my HCl as my departing moiety. And if I do the same thing using methoxide here, kick one of those down, one of the chlorides has to go, and then that gives us a vinyl chloride here, and still an H, and I can of course use the same O minus CH3 to get to the exact same product. So yeah, that's fairly easy, straightforward. You have your industrial processes, and then you have a largely impractical, because these reactions, the first step being fairly easy, second step being much harder, but that's definitely one way that you can make an alkyne. Now, what can you do with them? What kind of chemistry is available? And sure, we had already discussed Well, that proton up there, this proton, that's pretty acidic, right? So why not just deprotonate it? I mean, you could deprotonate it and make a base, right? So, or it could make a nucleophile and act like a nucleophile. So let's just go down here and say you've got an R, all right? So whatever the R is an alkyl group of some kind, H, and just throw in a base. And I like that base. It's a nice base. That just comes over here, deprotonates, electrons go back on that carbon, are out here, and now you've got a negative charge, okay? And that negative charge is free to be a nucleophile. It's pretty good nucleophile, actually. So if you've got something, we'll call it R prime, and it comes out to a Br. You know, I can do SN2 chemistry if the conditions are right. There's not a lot of steric inhibition there. It's a pretty svelte nucleophile, and then you get an asymmetric alkyne. So that produces an R prime. All right. And in this way, you can synthesize an internal alkyne. All right, because this is a terminal alkyne, right? So this is a terminal alkyne. And then you produce an internal alkyne where there's something on the other side, and I've made it so that it's, you know, these two R groups are potentially different. They could also potentially be the same. Depends on what you want to make, right? But of course, halogen displacement is not the only things. There are many different electrophiles. So, you know, anything that loves electrons will probably entertain the idea of reacting with a deprotonated alkyne. So let's consider forming another carbon-carbon bond with our deprotonated alkyne here. We got a negative charge. And what's a good electrophile? How about a ketone? All right, we've talked pretty extensively about how ketones are, they love electrons, and this negative charge is quite happy to go and attack that carbon right there, right between the R groups, and then that goes and kicks that pi bond up onto the oxygen, and you end up with an R double bond, and that connects now to a new carbon, and that goes to an oxygen that's deprotonated, an R group and an R group, all right? And so let's take a look at where our new bond is this is the new bond, all right? And our oxygen is here, so that's our oxygen, and then you can see our two R groups and how that bond is formed, okay? From that alkyne, that deprotonated alkyne. Of course, you can do the same thing with not just a ketone, you can do it with a formaldehyde. So formaldehyde, you'll remember, is got an H on the end instead of two R's, right? So this is the next oxidation up from an alcohol, as in formaldehyde, as an aldehyde, and then formaldehyde is just the name of the aldehyde that has no R groups. All of these things will give you carbon-carbon double bonds because they can all do the same sort of chemistry where that attacks there and that attacks there. And of course, the difference is your final products end up having a different number of hydrogens, right? So then this comes out, and that's an O minus with an R and an H, and then this is an R group. Comes out, and that's an O minus with an H and an H, and of course a triple bond. And then you would do the work up here. So, you know, you're not going to isolate an O minus. You're going to just add a little bit of H plus, and H plus will protonate, and that'll give you the alcohol. All right, so this is a good way to make alcohols from acetone or ketones and other carbonyl groups, right? Carbonyl groups are the carbon double bond oxygen groups. And so that is a pretty straightforward way in how you can use alkynes to make carbon-carbon bonds. Now, let's say you have an alkyne and you hate it. You just want to take it back, and you know you're just not into it. You're just not digging it. You just need to go back to something a little bit more reduced. All right. So reduction of alkynes is pretty straightforward. Actually, it's very similar to an alkene, right? So in a reduction, let's all remember, Leo, oh, no. No, I do oil rig. That's what I do. Oil rig. right? A reduction is gain. So this has to gain electrons in the sense that it's got to gain hydrogens, right? Because it's going to go to an alkane. That means it's got to gain, not protons. That's not a reduction. That's got to gain hydrogens with electrons associated with them. Okay. So what do we do in the last one? It's the same sort of business with the metal. Okay. You have a palladium surface. Platinum works as well. It's just like a surface out here. And then hydrogen gas gets stuck onto the surface because these metals are very good at absorbing hydrogen. And you end up with an R group that comes in, and you have a pi system, and you have your first pi system, right, coming in, and that's going to grab two of your hydrogens down there. All right, and there's your first two hydrogens, and then it comes back off, bloop, as an alkyne. All right, and now it's got a second pair of orbitals, and it's going to come back in, and it's going to grab a couple more hydrogens, and then it's going to bloop right back up there. What does that mean, of course, is that, again, just like in the alkyne business, the addition of these hydrogens happen on the same side, so hypothetically, the orange hydrogens on that side, on the left side of the molecule, these would have added at the same time, and the green hydrogens would have added at the same time as well. Now, that is a great way to go down to from an alkyne. So this is the alkyne to alkene, alkane even, alkane reduction. But what happens if you're not totally sold on the alkane reduction? You just kind of want to try an intermediate alkyne to, say, an alkene, right? You want to go to an alkene. Well, so you can do that. Alkyne to alkene. And that is done with a poisoned catalyst. All right. So the poisoning of this catalyst means that it is capable of doing the reduction of the higher energy. So the first of the triple bonds is pretty easy to do. Remember when I said, you do the first reaction that makes the double bond and all the way up here, right? So the double bond is pretty stable. The triple bond, that third bond, that's not very stable. It's actually pretty easy to go from triple to double bonds. And it's easy to go from single to double bonds. But that triple bond, it's got a lot of energy, and it's pretty easy to just sort of cut it off before you get all the way down to a single bond. So if you use something called Lindlar's catalyst. All right, in the presence of H2. So Lindlar's catalyst has been poisoned. Palladium catalyst deposited on calcium carbonate or barium sulfate. And then a little bit of lead is added, or sulfur, I guess. And the lead and the sulfur essentially rob it, if you will, of its ability to take on that second reduction. It cannot reduce, Lindlar's catalyst cannot do, say, a reduction from an alkene to an alkane, but it can do an alkyne reduction to an alkene. Now, Lindlar's catalyst, of course, gives you one stereospecific product because it's the same sort of thing. It's palladium, lead, lead, and so it's got hydrogen still coming off of it, just like before. And let's just do it. We get this, and so now we're going to have a same sort of deal, an approach that involves the pi bonds here and the pi bonds here, and yeah, you got pi bonds coming up in here and up in here, and it's going to grab the first one it sees, and it's going to grab these, say, for instance, right? So it's going to go down here, down there, down there. And these concerted looking reactions where everything gets added all at once, they have a tendency actually to form things syn addition-wise, and they add to the same face, which means Lindlar's catalyst always gives you a cis alkene. All right, because it's always going to add the hydrogens to the same face. Same argument that I made up here, even though it's basically irrelevant because it doesn't matter. It's going to add 2 hydrogens, and they're not going to be any sort of, there's no stereochemistry that you'll be able to discern from that. The point is that it does the same thing. It adds 2 hydrogens to the same bonds. It's both added to that orange orbital, and so you end up with a cis double bond. Now, if you wanted to not have a cis, let's say you wanted to have a trans double bond, you wanted to go from an alkyne to an alkene, you can actually do that too. That process uses a dissolved metal reaction, and so these are actually really fun reactions. If you ever have an opportunity to run one, you will probably enjoy it. They usually turn deep color blue. Solution is if you take metal, sodium metal, and throw it in ammonia, you will get the trans product. All right, and the trans product, as you've probably noticed, when you see a trans product, usually occurs through some sort of stepwise, as in something happens first to give you something, and then something comes and finishes it off, largely driven by thermodynamics, as in getting those R groups away from each other. Usually you find a syn product when everything happens all at once. Think that osmium oxidation from the alkenes, right? That happens all in one phase. Magnesium permanganate, all in one phase, right? So it gives you the syn product. The anti-product often occurs stepwise, and that's what you see here. So this comes down here, right? And so when you mix sodium in with ammonia, you end up generating the sodium radical. All right, and so that's essentially now going to be able to do a radical abstraction from your alkynes. Let me just redraw that alkyne here. Okay, and that's going to come in. And 1 electron from the alkyne in the triple bond is going to go up here, and then 1 reaction is going to go down there. And so what you're going to end up with then is something that is actually pretty unstable. This double bond here, and you've got a radical anion, radical on that side. All right, actually, let me erase that because it's on the same side. So what we end up with is the radical anion is actually over here, and then there's a radical on that side. Now this is not stable. First of all, these 2 R groups are close together, and it's allowed to interconvert. So this is an intermediate, and you can have an equilibrium process here that greatly favors the rotation or the interconversion. So this is a double bond, right? And normally you don't see rotation around double bond, and this will be covered more in OChem 2, but this can break in a double bond and then reform, and then that will give you a trans system. All right, and that forms right again. You end up here with your negative and your dot right here. Okay, and this, so you have a sodium dot, right? And you still got this ammonium up here, so that's partying somewhere around there. That negative charge is eager to go and grab a proton. So you've got NH2H, and then this thing's like yoink. All right, and that at least satisfies the negative charge, but you still have this really pretty reactive radical right here. Okay, you have another sodium radical, and sodium doesn't want to be a radical. Sodium doesn't even want to be negatively charged. Sodium is always looking to give up its radical, okay? So I guess it's probably something I should fill you in right here. This electron is not, sodium's getting rid of it, right? So what comes off here actually is sodium plus, okay? The sodium salt. And it's going to do it again here. It's going to say, hey, bud, have my electron. And it's going to be like, oh, if you're giving them away. And then it's going to be a full-on negative charge, okay? And one more equivalent of your ammonium was going to come in, deprotonate, and there you go. You end up with your trans double bond, and you have, oh boy, that was a big scroll. You end up with sodium, pretty basic solution, sodium amide. And so these reactions occur in a solution. So this is deprotonating ammonia, which we saw was a pretty strong base, and it's deprotonating them to give you a really strong base. So this reaction is not going to do super well if there is going to be something that can be deprotonated super easily, but it is a neat way to make the trans double bond, okay? So that's what you really want to be. This goes to trans, all right? And that is a good way to take these things and interconvert, keep making hydrocarbons.